In this video, I'm going to talk about the RC phase shift oscillator circuit. And you can make this circuit using a single NPN transistor. So let's begin. We're going to need 3 capacitors in series with each other. And then we're going to need at least 3 resistors that connects each of these capacitors to ground. Next, we're going to connect this to our NPN transistor. And we're also going to have a voltage divider network across the base of that transistor. So let's call this RB since it's attached to the base of the transistor, and let's call this RA just to distinguish it from the first one. The emitter of the transistor will go straight to ground. This is the base, this is the emitter, and this is the collector. RB is going to go directly to the collector, and then we're going to have another resistor, RC, or the collector resistor. And then the output will be taken from the collector of the NPN transistor. Now, we need a feedback capacitor, which will be here. The value of this capacitor isn't too significant. As long as it's large enough, the circuit will work. So in my example, or in my experiment, I used a 100 microfarad capacitor for, we'll call this CB, a bypass capacitor. For the bypass capacitor at the output, I've used a 1000 microfarad capacitor for that. RC is connected to the positive voltage supply. In this case, I use 9 volts for this circuit. And each of these 3 capacitors, I kept it the same, so we can call it C. And these 3 resistors, I kept the value the same, so we'll call it R. Now, when C, that is all 3 of these capacitors, when it's set to, when I use a 0.1 microfarad capacitor for each of them, and for R, I use a 2.2 kilo ohm resistor, the output frequency that I got was 294 hertz. Now, by the way, initially this circuit generated there was a lot of instability in this circuit. To make it more stable, I had to put a 10 picofarad capacitor at the output of this circuit. By doing that, I was able to generate a more stable sine wave. So I want to make sure I mention that important fact. Now I got this frequency at these values, and RC was set to 1 kilo ohm. RB, I use a 100 kilo ohm resistor for that. And for RA, I use a 470 kilo ohm resistor. RA needs to be at least 1/3 of RB or more. If RA is too low with respect to RB, VB may not be high enough to activate the transistor because you need at least 0.6 volts between the base and emitter to activate it. But in this example, I've set RA significantly higher than RB so that the base voltage will be more than enough to activate the transistor. In other words, you want to make sure that this condition is met, that the input voltage, the voltage of the power supply, which in this case is 9 volts, times RA over the sum of RA and RB. This is the voltage divider formula. This needs to be greater than VBE, in this case, more than 0.7. Otherwise, the transistor will be off and the circuit will fail to oscillate. So in this example, RA is 470K, and the sum of RA and RB is 570K. The voltage at the base, or at point B, is going to be 9 times 470 divided by 570. So if the transistor wasn't there, the voltage at this point would be 7.42 volts. Now, because the transistor is there, it's going to absorb some of the current from that voltage divider network, and so the actual voltage will be less than 7.42. The extent to which it deviates from 7.42 depends on how much current it's pulling away from that voltage divider network. But this is significantly higher than 0.7 volts, so the transistor will remain on. Now, the next thing we need to talk about is calculating the output frequency. And for the RC phase shift oscillator circuit, you can calculate the frequency using this formula. It's 1 over 2 pi RC times the square root of 2n, where n is the number of RC stages that you see here, which in this case we have 3. So for this particular example, the theoretical frequency is going to be 1 over 2 pi. R is 2.2 kilo ohms, so that's 2200 ohms. C, I'm running out of space here, is 0.1 microfarads. Now, the average value of these 3 capacitors when I measured each one individually is actually 0.106 microfarads. So that's 0.106 times 10 to the minus 6. And then, since we have 3 stages times 2, this is going to be times the square root of 6. So put all of this in a parentheses if you're going to type that in to your calculator. So the theoretical frequency for this circuit, according to that formula, it's 278.6 hertz, which is not too far away from the measured frequency of 294 hertz. Now, one thing I forgot to mention is the specific type of NPN transistor that I'm using in the circuit, and it is the 2N4401 NPN transistor. Now, for those of you who may want to try this circuit, here's some other values that I've used that cause this circuit to oscillate as well, in addition to what you saw previously on the board, which I'm going to rewrite shortly. So when R is set to 2.2 kilo ohms and C is 0.1 microfarads, which the measured value is 0.106 microfarads, the output voltage was 3 volts. And as mentioned before, the output frequency was 294 hertz. Now, it wasn't a perfect sine wave, but for the most part, it looked like a decent sine wave. Now, the next trial that I tried was using a 1 kilo ohm resistor. C was the same, so 0.106 microfarads. The output voltage was 2.2 volts. It went down. This is not the RMS voltage, by the way. This is the peak voltage. Now, the frequency increased to 491 hertz, which makes sense because the frequency is inversely related to R. So as you decrease the resistance of the RC network, the frequency is going to increase. And the reason for this is because R is in the bottom of the fraction, and so there's an inverse relationship. Whenever you increase the denominator of a fraction, the value of the whole fraction goes down. So as R goes down, F goes up. And as we can see, as we decrease the resistance from 2.2 kilo ohms to 1 kilo ohm, the frequency increased from 294 hertz to 491 hertz. Now, in another trial that I've tried, I used a 4.7 kilo ohm resistor. This basically stayed the same. The output voltage went to 3 volts, and the frequency decreased to 196 hertz. So increasing the resistance of the RC network led to a decrease in frequency, going from 294 to 196. Also, R affects the overall amplitude of the output signal. decrease in R from 2.2 to 1 led to a decrease in the peak output voltage of the sine wave. So that's something else to take into account. So if you set R too low, the output voltage may be reduced to such a point that the oscillations may fail to occur. Now in another trial, I set R to 3.3 kiloohms and I used 3.47 microfarad capacitors, which the average measured value was 0.456 microfarads. The output voltage was about 3 volts peak to peak, and the frequency that was measured was 51.7 hertz. So this circuit is quite useful if you wish to design a 60 hertz sine wave generator, because I was close to 60 hertz. I just need to tweak the circuit a bit. In fact, you can replace one or two 3.3 kilo ohm resistors with a 2.2 kilo ohm resistor, because as you decrease the resistance of the RC network, you can increase the frequency. So that might boost it up to 60 hertz if you want to design a 60 hertz sine wave oscillator with this type of circuit. So that's it for this video. Now you know how to design the RC phase shift oscillator circuit, and you have some values that you could start with. Thanks for watching. Actually, there's one more thing that I forgot to mention, and it's very important for those of you who may want to build this circuit, and that is the ability to tune this circuit to the appropriate frequency that you want. Now, since R and C controls the frequency of the circuit, you want to tune one of those devices. Now, it's hard to find a variable capacitor that you can tune in the microfarad range. There's variable capacitors that tune up to 100 picofarads, some that may go up to 400 picofarads, but it's hard to find one that goes up to 1 microfarad. However, you can tune the resistors in a circuit using a potentiometer. What you want to find is a triple gang potentiometer. That's one where you can adjust 3 resistors simultaneously at the same time, which is perfect for this circuit. So all 3 resistors will be adjusted accordingly using a triple gang potentiometer. So you may want to look into that if you decide to design a circuit.